For this module, we're going to have three main videos. We're going to start by looking at the products of elimination reactions and then the mechanisms of those reactions. We will then have a separate video on nucleophiles versus bases. Then we will start to predict the products of reactions. So the products of elimination reactions are alkenes. What we're going to eliminate is a hydrogen and a halogen. So when we eliminate that from an alkyl halide, because we are still reacting alkyl halides in this module, what we produce is an alkene. So removing these items will produce a new pi bond. Now an acyclic alkene, that means in a line, will have a general formula of CnH2n. So if I have an alkene like this, and they're named a lot like alkanes, I'm going to number my alkene, longest carbon chain that includes that functional group. That alkene, that double bond, is that functional group. And then I name it. Now if this was an alkane, it would be hexane, but it's not. It has a double bond. So I delete the A from hexane and make it hexene. But I have to give that double bond, that pi bond, an address for where it starts. And it starts on carbon 1. So this is an example of 1-hexene. Now if I have that 1-hexene and then I start to give it a couple of methyl groups, then I'm going to name it as if I was naming an alkane. Again, first hexane, then I'm going to identify where that functional group is, give the functional group the proper ending. Now I'm going to talk about my functional groups here, not my functional groups, my substituents. Here, all three of them are methyl groups. So this would be a 2,3,3 trimethyl 1-hexene. So you see the names shake out an awful lot like an alkane, but this time we have to give that double bond an address. We also have some geometric isomers that occur with our alkenes. Because that pi bond gives a rigid structure for the carbon, and what I have here, these are my pi orbitals for overlap, so this is one pi bond. And then this is a sigma bond, and then I have, where'd it go? Then I have my hydrogens, if I'm going to do a non-substituted. And so these remaining orbitals hybridize. The hybridization here is sp2. These carbons are sp2 hybridized because this one p orbital on each of the carbons is occupied. Well, that leaves the rest of the substituents here in a trigonal planar geometry. That trigonal planar geometry creates geometric isomers. Now, if there are two hydrogens and they're on the same side of that pi bond, then we have what's called the cis isomer, and we saw this in a previous module. If those hydrogens are on opposite sides of that double bond, then we have what's called the trans isomer. Now, if those two hydrogens are on the same carbon, then you don't have is a terminal functional group. You have a terminal alkene. Terminal means it's at the end of the chain. So this is a terminal alkene. Now if you have an alkene that has 2 or 4 different groups, then we need to assign priorities to those groups. Similar to the way that we assign priorities to around an asymmetric center with our CIP priority assignments. We will assign a high and low to each of the groups on each of the carbons. So if we have high and low on the same side, then we're going to use the prefix Z. Z means same. If we have opposite, so the high and the low are on opposite sides, then we assign the prefix E. Now when we assign this prefix, we're going to put it in parentheses with the number of the bond. So whatever address you gave in the naming, for example, if we have, let's go back to hexene, but let's put it here. So here we have 2, 3, 4, 5, 6. So this, as it's drawn, this is cis, no, it's not, it's trans 2 hexene, because my hydrogens that are implied are on opposite sides of the bond, opposite sides of the pi bond. So now I have to assign a high and a low. So on the first atom, I'll color it green. On my green atom here, my methyl group is going to be high, and my hydrogen group is going to be low. Hydrogen will always be the low group, because we're going to assign priorities first by atomic number, and then if there's a tie, we're looking for the atom of difference, just like in a CIP priority assignment. So if I change my color, let's make it red. So for the red carbon, then, here I have a CH2, here I have a CH2, so far we're the same. Here I have a CH3, here I have a CH2, but it's bonded to another carbon. So this is going to be the high, and this is going to be the low. So here, I will name this, it's still a hexene, but I'll go through all of the steps. If this was an alkane, it would be a hexane. It's not an alkane, it's an alkene, so I'm going to put the ENE and then give it an address. It's going to start at carbon 2. This carbon 2 has an ethyl, or excuse me, carbon 3 has an ethyl group. So this is going to be 3-ethyl 2-hexene. Now, I need to say which order this is. So because my highs are on opposite sides, my lows are on opposite sides, and the double bond starts at carbon 2, this is going to be a 2E in parentheses dash 3 dash ethyl dash 2 dash hexene. Now, as I have mentioned before, there is a convention where you put the number right before the suffix. I'll count that correct as well. Either way works for me. If you've already learned it one way, go with that way, because that's the way your homeschool does it. Keep it that way. Now, when you have an alkene, the alkene, and I understand this is sideways, work with me, the alkene is found right here. So if you have other functional groups, it's possible that you'll put the "ene" in there, and it's possible that you'll need to use it as a prefix. In most cases in this class, you will be using the "en", even if there's an additional prefix. For example, if you have an aldehyde and an alkene, I'm going to run off the page here, like this, we would number with the aldehyde being the priority position. So the aldehyde gets carbon number 1. So this is a hexanal if it's an alkane, but it's not. We replace that A with an E and give it a number. We would call this 4-hexenal. That "ene" is what's getting the 4. So here we have a complicated suffix. It's like a double suffix. You'll get used to it with more practice, but always ask questions if you come up with something in the classroom that doesn't quite look like you expect. Now, generally speaking, the stability of an alkene, you will have a more stable alkene when you have more substitution at that pi bond. So here we have an unsubstituted alkene. That's going to be your least stable situation. Here we've replaced one of the hydrogens with an R. Here we've replaced 2. Here we've replaced 3, and this double substitution, this is in the cis conformation. Typically trans is going to be more stable than cis. So here we have 3, and here we have our 4 substituted alkenes. So remember, organic chemistry, the majority of our reactions are going to be stability driven. So when you go to predict products, the majority of the time, you will be looking for the more stable alkene. Of course, it always works this way for those exceptions as well. Now remember, with a cyclic alkene, and I don't think I covered this with my cis and trans, but with a cyclic alkene you can also have cis and trans. When you have a trans cyclic alkene, you end up with this twisty structure. They are isomers. We're still looking at an 8-membered ring here, but because the hydrogens are on opposite sides, it makes it twisted. Now there is a reference here to the enthalpy. You do not need to know the enthalpies, but I'm going to show you the enthalpies just to hammer in the point. Here's your non-substituted alkene. The higher the enthalpy, the more stable it is, because the more energy it takes to remove whatever it is. So here, although these are negative numbers, note the trend. The enthalpy gets greater as you substitute. So the higher the enthalpy, the more stable the situation. So now let's look at our reactions. Like SN2 and SN1 that we covered in the previous module, we have these two different mechanisms. So for the E2 reaction, this is a concerted reaction. It all happens at one step. And this particular, let's see if I can write over this, this particular file has the alpha and the beta in the wrong place. So I'm just going to correct that real quick. So the carbon that has the halogen, we're going to call that our alpha carbon. And the carbon next door that has a hydrogen that's going to be removed, we're going to call that our beta carbon. Beta is next door. Now you see we have a base that comes in and he's coming after this hydrogen. He's coming after this hydrogen because this bond here is vulnerable. When he takes that hydrogen, then the electrons are going to fall down to create a new pi bond here that pushes that leaving group off. All of that happens at once. So the kinetics here, this is a second order because the rate is going to be related to the concentration of both the base and the alkyl halide. For the E2 elimination to occur, the beta hydrogen needs to be anti-periplanar in relation to the leaving group, in relation to our halogen. And what that means is our base can only come in and grab one of these hydrogens if it's pretty far away from this leaving group, because the leaving group has a whole bunch of electronegativity to it. So the base can't get in this way. And if it does, or this way, if this was a hydrogen. So we look for an anti-periplanar beta hydrogen. Now that's easiest to see with something like a ring structure. So if we look at a hexane of sorts, and I put a halogen here in the axial position, I'm just going to put a hydrogen over here. And over here on this carbon, I'm going to put, let's see, then I would be down. I'm going to put a methyl group here, and then I have a hydrogen equatorial here. And usually we want our big bulky stuff to be on the equatorial position. Well, maybe we're being forced to have methyl in the axial position here because we have a T-butyl group. That T-butyl group will really want to be equatorial in order to stabilize this ring. So the only way this elimination will occur is if I have a hydrogen here in this axial position. This is anti-periplanar. That way the base can come in here, which drops these electrons down, which shoots this guy off. That's the only way that can occur. If, for example, we had a methyl group that was axial here and a hydrogen here, we're not going to have a reaction with this conformation. We have to have that hydrogen group anti-periplanar. So this is the only reactive beta hydrogen. In the E1 elimination, we're going to make that carbocation first, and the carbocation is going to be your alpha carbon. Then you're going to look at your beta carbon, remove the hydrogen, drop that down, and then you form your alkene. E2 reactions are going to happen with our primary, secondary, and tertiary alkyl halides. Now we'll talk about, because these are what we reacted with substitution as well. In the next video, we'll talk about when things act as bases and when they act as nucleophiles. The rate, as I mentioned, will be dependent on the concentration of both the alkyl halide and the base. And the base is going to remove a proton. So we're looking at that alpha. Goodness gracious, that alpha and that beta carbon. So we will have some strong bases. I want you to ignore this part right now. We called those electrophiles before. But depending on the conditions, they will act either as a base or as a nucleophile. Now, like all reactions, the more stable product is usually what will be preferred. In order to stabilize an alkene, we will want what's called an internal alkene. Here I've been using, let's see, 2, 4, there's 6. We've been using this as an example. This is 1-hexene. That's called a terminal alkene. You see how the double bond is here at the end. The more stable alkene, there we are. The more stable alkene would be our 2-hexene. And that's more stable because it's inside. Remember those enthalpy values. Now there's a rule, and it's called Zaitsev's rule. And Zaitsev's rule states that the more substituted alkene is obtained when the hydrogen is removed from a beta carbon that is bonded to the fewest hydrogens. Well, what does that mean? That means we want to form internal alkenes if we can. Now, Zaitsev's rule is a shortcut, but it is not always the case. Again, it always works until it doesn't. What we have is called a conjugated alkene. Now, a conjugated alkene is a special case, and it looks like this, where you have alternating double and single, double and single. And this is a special stability state. So if you're moving on organic 2, either here or somewhere else, or even in biochemistry, this is something you may need to know. Even the MCAT, you may need to know this as well. Now, a steric hindrance can also dictate major products of an E2 reaction, where you end up with this not necessarily most stable alkene. So we'll have to pay attention to not only how bulky is the base, but is it acting as a base or a nucleophile? What's the order of our alkyl halide, and all of those things. We'll bring that all full circle in a moment. Now, alkyl fluorides do break the rules. I doubt you're going to see alkyl fluorides in my class, but this is something that you're going to need to pay attention to, taking the MCAT, the PCAT, or moving on to chemistry somewhere else, including biochemistry. So you might want to commit that part to memory for someone else. E1 reactions are unimolecular reactions. This is where we're going to make our carbocation. We can only do this with secondary and tertiary alkyl halides, and only under special conditions with a weak nucleophile, weak base. So we're looking at solvolysis reactions here. We're looking at reacting with water and with alcohols. Now, this will follow Zaitsev's rule. It will follow Zaitsev's rule because we're forming a carbocation.